Welcome back everyone. In this lecture, we will actually study the representations of sln+1 C. So, we will use the notations that we developed in the last lecture. So, let us actually recall the very important representation called adjoint representation. So, if we take G to be sln+1 C, then G acts on G via the add map. So, that gives you the adjoint representation. So, one can actually restrict that representation and then make H acts on G. Okay. So, if you look at this action, then this action is indeed semi-simple. Okay. So, what we mean by semi-simple? So, each element of H must act diagonalizably on the representation, and since H is being abelian, so one can actually simultaneously we can diagonalize the action of H. Okay. That kind of action is called semi-simple action. So, now we have this action. So, this is acting semi-simply. So, in particularly if we take if we look at the action and then see that what will be the simultaneous eigenspace, which also will be called weight space. So, let us actually define. So, it is clear that G will be written as direct sum of G alpha coming from H star, where the G alpha is defined to be simultaneous eigenspace for the action of H. So, this is those x in G such that the bracket Hx is given by alpha of Hx for all H in H. Okay. And of course, I gave it left it as exercise, but let us just work it out. So, if we take these weights of this adjoint representation, which is those alpha in H star such that G alpha is being non-zero. So, this is going to be exactly equal to 0 union phi, where recall that phi is nothing but given by epsilon I minus epsilon j, where 1 less than or equal to j less than or equal to n plus 1. So, now how one can verify this? So, note that this H is given by span of Hi. Okay. So, to understand the action of H, it is enough to understand the action of Hi for each I. So, recall Hi is given by Ei minus Ei plus 1 I plus 1. So, now if we take for example, some element inside this H, so then this H can be written as some A1. So, maybe we can use epsilon I basis sorry Ej basis, then the computation will be much more simpler. So, if we take H, so that is going to be A1 E11 plus etcetera plus A n plus 1 E n plus 1 n plus 1. Okay. So, this is going to be the H such that this A1 plus etcetera plus A n plus 1 is given to be 0. So, the sum of the diagonal entries are 0. So, now if you take for example, this alpha inside phi, okay, and then look at what will be the G alpha space. Let us call it alpha being epsilon I minus epsilon j. So, we can just simply assume that I is less than j. Okay. If I is greater than j, we can simply consider minus alpha. Okay. So, for alpha, so we are going to look at this Eij. So, let us see how H acts on this Eij. So, if you do the computation, then you can easily see that this is H Eij minus Eij H. Now, H being the diagonal term, so H is nothing but A1 E11 plus etcetera plus A n plus 1 E n plus 1 n plus 1. So, you can easily see that. So, only for this product I will survive. So, this thing will survive. So, this is going to give you AI times EAI times EIJ, which is EIJ. So, this is going to be AI EIJ minus, for this you will be getting contribution from EJJ. So, you get EAJ EIJ. So, then this is exactly AI minus EAJ times EIJ. But if you think about it, AI is nothing but ith projection of H. So, this is exactly epsilon I minus epsilon j acting on H EIJ. So, this simple calculation tells you that these EIJ, they corresponds to the form epsilon I minus epsilon j. So, EIJ indeed corresponds to the root epsilon I minus epsilon j. So, now if you take elements of H, then you can easily see that they all commute. So, in particularly the elements of H corresponds to the 0 weight. So, indeed this calculation simply says that if you take these basis elements Hi, I range from 1 to n. So, this corresponds to the weight 0, and if you take this Eij for I not equal to j from 1 to n plus 1. So, this Eij corresponds to epsilon I minus epsilon. Since this will form a basis, so that actually proves the claim that we made. So, this claim follows from the fact that these elements will form a basis, because they are all indeed root vectors. So, since they form a basis, so that gives you that these are all the only roots. So, this is a basis of G. So, in particularly what we have, so we have this action of H that is semi simple, and we also can actually simultaneously diagnose the action of H. So, then we can talk about these root spaces with respect to that. And we observe that those roots are actually has very explicit form. Okay. So, let us make one simple observation. So, this is something we made it already. So, Sn plus 1, which is the group generated by this Si, okay, that is how we are identifying. So, this is naturally acting on this set of roots phi. Okay. So, this is very important. And the second thing, the dimension of this G alpha, so that is 1 for all alpha in phi. Okay. And the dimension of G 0, which is the dimension of H, so that is exactly m. Okay. And note that if we take, okay, maybe you can take it as exercise. So, all elements in phi are indeed Sn plus 1 conjugate. That means, if you give any two elements in phi, you can find some Sn plus 1 element that takes one element to another element. Okay. So, this is indeed some important observation that we made about adjoint representation, and similar observation actually true. Similar statements are true for any finite dimensional representation. So, that is what we are ultimately going to prove. So, then the very first natural question, so what about the action of H on the any given finite dimensional representation? So, let us actually look into it. So, let us start with V being just a finite dimensional G module. So, recall H is there. So, this is the carton, okay, sitting inside G. Okay. So, what we will do, we restrict the action of G to H. So, that means I am looking at, let us call this pi. So, this is the map from G to GL of V. I am restricting pi to H. So, you get a map from H to GL of V. So, if you take some x here, you can actually write this x V here. So, each element H in H, and I am actually looking at the H V, which is a map from V to V. Okay. So, how it acts? So, we want to know. Okay. To understand this, of course, we invoke the representation theory of SL2 and then use that information to conclude everything about the action of H. Okay. So, recall that there is this natural subalgebra which is Si. So, this is generated by Xi and Ya. So, which is isomorphic to SL2 of C, and this is there for each I. Okay. So, what is Xi? Xi is given by Ei plus 1 and Ya is given by Ei plus 1 I, and the bracket being Xi Ya is exactly equal to Hi, which is Ei minus Ei plus 1 I plus 1. So, now what we do? We take this representation V and then restrict this to Si. Okay. So, then you can see that. So, this is indeed a representation for this SL2 copy, and this is a finite dimensional representation. So, this becomes finite dimensional representation for Si. Okay. Now, since Hi is actually plays the role of H in this SL2 copy, so using the SL2 representation theory, we conclude the following. So, using the SL2 representation theory, we see that the action of Hi on V is diagonalizable, and not only that, any finite dimensional representation of SL2 is indeed completely reducible. So, it can be written as the direct sum of irreducible representation. For each irreducible representation, we know that the action of H actually, the eigenvalues of H are integers. So, in particularly, so the eigenvalues that corresponds to this operator Hi, so that will be integers. Okay. So, this is A and then B, the eigenvalues of this operator HIV are integers. Okay. So, now since Hi acts diagonalizably for each I and H being abelian, so you can easily conclude that the action of H on V is diagonalizable. Okay. So, since H is abelian and Hi form of basis for H, we can conclude that the action of H on V is semi-simple. That means it is simultaneously diagonalizable. Okay. So, we have started with general finite dimensional sln+1 module, and then we have concluded that the Cartan acts semi-simply on that. So, in particularly we can talk about the weight space decomposition. So, that is the simultaneous eigenspace decomposition. So, we can define this direct sum of V lambda lambda in H star. So, where this V lambda is given by those vector in V such that the action of H is given by lambda of H for all H in H. Okay. So, this is called weight space decomposition. Weight space decomposition. And of course, generally V lambdas are called weight spaces, but we will be only interested in the spaces which are non-zero. So, that is why we can write down the weights to be Wt of V. So, this is the set of weights, the set of weights of V to be the those lambda in H star such that this V lambda being non-zero. Okay. And for any given lambda in the weight, so the dimension of this V lambda, so this will be called the multiplicity. So, this is the multiplicity of the weight lambda inside capital V. Okay. So, these multiplicities again play a very big role in the representation theory. Okay. And so, these spaces V lambdas, so they are called weight spaces. So, since we have fixed the carton, we are not actually referring to H weight space and so on, we can simply call it as weight space. So, now you can easily see that, so what will be the eigenvalue of Hi. Okay. So, since we if you take some vector non-zero vector in V lambda, okay, for lambda in the weight of V. So, we have, okay. So, what will be the action of Hi on V? So, this is given by lambda of Hi V. Okay. So, since all the eigenvalues of Hi, they are all integers, we can conclude that. So, these are indeed integers. So, these are all integers. Okay. So, basically we are not interested in some general forms that comes from H star. So, we are interested in the forms on which for them like lambda of Hi must be integers. So, they are called integral weights. Okay. So, let us define this capital lambda. So, this is those lambda in H star such that lambda of Hi being integer for all I range from 1 to n. Indeed, what we proved that if we take V is finite dimensional G module, so then the weights of V is indeed subset of lambda. So, this is the immediate corollary. Okay. So, not only that each element of H acts diagnostically, all the eigenvalues of H must be integers. Okay. So, since H spanned by this Hi, so we have the simultaneous action. Okay. So, that is what gives you the weight space decomposition. So, we to understand given representation, it is important to understand the weight space decomposition and the weights that occur and the multiplicity that can actually the dimension can take, okay, the weight spaces can take. So, we will see later that indeed given any representation will be determined by that particular information, the set of weights and its multiplicities. Okay. So, here is more observation. So, if we take V being finite dimensional G module, so we already concluded that the weight of V must be subset of lambda, which is called the weight lattice. So, this is called the weight lattice. So, we can easily see that the cardinality of this the set of weights of V must be finite. So, that is because V being finite dimensional. So, if we take vectors from the different weight spaces, that set must be actually linearly independent. So, that forces that the set of weights must be finite for any given representation, finite dimensional representation V. So, now we will actually use SL2 representation theory to conclude more about these weights. Before that, let us actually see some examples. So, we already seen that if we take the adjoint representation. So, take V being the adjoint representation. So, then the weights of V were given by 0 union phi, given by the roots plus the 0. So, if we take the trivial representation, V being a the trivial representation, trivial one dimensional representation, then it is easy to see that the weight is just given by the 0 weight. And if you take for example, the natural representation C power n. So, this is the natural representation. Then one can easily see that the weight of this is given by this epsilon 1 etcetera epsilon n plus 1. Okay, this is just comes from the matrix multiplication. So, if you take for example, this H inside H and write it in terms of the epsilon I basis, that means Eij basis. So, this is written by A1 E11 plus etcetera plus A n plus 1 E n plus 1 n plus 1. So, then this H and on Ej. So, let us say Ej is the standard basis. So, V is spanned by Ej, where j range from 1 to n. So, then this H Ej, if you just this is the usual multiplication. So, this is the usual matrix multiplication. If you use that, then you can easily see that this H Ej is indeed given by Aj Ej. So, which is nothing but epsilon j of H Ej. Okay. So, that is why you get epsilon j's as weights of this V, because Ej's will form a basis for this natural representation. Okay. So, now if you take the dual, I will leave it you to check. Okay. So, if you take the dual of this natural representation, then the weight of that is going to be minus epsilon 1 etcetera minus epsilon n plus 1. Okay. Note that these representations are irreducible representations of G. Okay. So, we are going to make a proportion, actually that is actually going to tell you everything about the weights, okay, of all interesting representation that we have constructed so far. So, here is the proportion. So, if you start with the finite dimensional representation, then we have already seen that there are many ways to actually get new representation out of old representation. For example, we can take dual, we can take tensor products, we can take symmetric products, we can also take alternating products and so on. Okay. So, it is natural to ask what will be the weights of this new representation in terms of the old one. So, let us make this observation. If you take V being finite dimensional G module, so then if you take V star, the weights of V star is going to be just minus lambda, where lambda comes from the weight of V. Okay, it is basically minus weight of V. So, this is actually a quick check. Recall, if you take V in V lambda, X in G and F in V star. Okay. So, let's take, so let's take X in G and then so we want to conclude what is the V lambda star. So, let us do the computation. So, recall that X dot F defined on any V is going to be minus F of X V. Okay. In particularly, if V comes from V lambda, so then you can easily see that this X V is going to give you lambda. So, let us say H X is coming from H. So, then X V is given by lambda X V. So, that is to give you minus F of lambda X V. So, that lambda X V comes out, then it gives you minus lambda of X F of V. And since so this is true for V in V lambda. Okay. So, you have to actually choose this dual basis, and then so you choose this f actually, let us say, comes from the v mu star, which is the dual. Okay. So, basically you have to fix the basis and then take the dual basis of that and then work out this thing. So, now okay, anyway whatever we did here indeed tells you that if you choose this f carefully from the dual basis, then this formula indeed tells you that the weights of V star is exactly minus of weight V. Okay. And not only that, it is easy to see the dimension of this V lambda star is going to be exactly equal to the dimension of V minus lambda. Okay. So, I will leave it you to check this. Now, if we take the tensor product, let us say V and V dash being 5-dimensional G modules, then you can actually take the tensor V dash and then look at its some muth weight space. Then this is going to be just direct sum of V gamma tensor V mu minus gamma, where gamma runs over all H star. Okay. So, you basically take all possible tensors V gamma tensor V mu minus gamma, where gamma running over H star, you take all the direct sum of these tensors, that is going to be your muth weight space of V tensor V dash. So, one way to check is just start with the basis of V comes from the weight space decomposition of V, and then take again basis of V dash that comes from the weight space decomposition of V. So, let us say that V I, so this is the basis of V comes from the weight space decomposition of V. What do you mean by that? You take this decomposition, V is written as direct sum of V lambda, lambda comes from this H star. Now, you can choose a basis of V lambda and then put them together to get the basis of V, that is the basis that we are talking about here. And if you take the V I to be the basis of V comes from this weight space decomposition, and then W j being again the basis of V dash again comes from the weight space decomposition of V dash, then it is not hard to see that V I tensor W j. So, this becomes a basis of V tensor V dash, again this also comes from the weight space decomposition of this V tensor V dash. So, what is the weight of this? So, if you take x in H and then compute how x acts on V I tensor W j. So, since it acts as derivation, so it is x V I tensor W j plus V I tensor x W j. So, now you can easily see that x V I is given by lambda of V I, lambda of x V I. So, if V I comes from let us say V lambda and then W j comes from V dash mu, then x W j is given by mu of x W j. So, if you use that here, then it is exactly lambda plus mu of x V I tensor W j. So, in particularly the weight of this tensor V I tensor W j is lambda plus mu. So, V I tensor W j sits inside V tensor V dash lambda plus mu. Okay. So, this tells you that all these are weight vectors, and since that form a basis for this tensor product, so that actually tells you that we have this decomposition. Okay. So, this way we are actually getting some information about the weights of these dual tensors and so on using the weights of V. So, I will leave it to you to think about what will be the weights of symmetric product and alternative product and so on. So, here is the third statement. Suppose V dash is a submodule, then what happens? It is a G submodule. Maybe you should take it as exercise, then it is easy to see that this V dash is written as direct sum of V lambda intersection V dash, where lambda runs over H star. Okay. So, where V is given by this weight space decomposition, V equal to direct sum of V lambda, lambda in H star. So, if you know the weight space decomposition of capital V, then from that you can actually get the weight space decomposition of V dash by just taking the intersection. Okay. So, this is a simple exercise that you can actually do. Okay. So, I will actually stop here. So, we will continue with the discussion of this finite dimensional representation of sln+1 in the next class. Thank you. I will stop here.